Okay, so good afternoon, everybody. We are going to begin with chapter number 8 today. Chapter 8 deals with the central processing unit. Can you see my screen?
Yes, yes.
Right. So on your screen, you can see now the major components of the CPU. This is something that we have discussed very often. Repeatedly, I have gone through this, but for the sake of completeness, I'll do it once again. So what is the CPU composed of? The CPU is composed of basically three major components: the control unit, the memory unit, which actually consists of a set of registers. Registers are very fast buffers, okay? They are made up of flip-flops. So an n-bit registers would be constructed by n flip-flops, by a combination of n flip-flops. Then the third component is the arithmetic logic unit. As the name suggests, the arithmetic logic unit is responsible for the computational part that is required to be carried out in the instructions. So all the arithmetic computations as well as the logical computations such as OR, NOR, NOT, and XOR, XNOR, etc., they are carried out by the ALU apart from the arithmetic operations such as plus, minus, divide, multiply, etc. Right. Now, in this chapter, next what we are
Excuse
going
me,
to
ma'am.
see is, yes,
Ma'am, a student is asking to let her in. Shweta.
okay, yeah. So, what we are going to see next in this chapter is we are going to have a peep into how these registers set, these set of registers actually are able to communicate with the control unit and the ALU. Okay, that entire deep, insight of the functioning of the central processing unit is what we are going to see next now when we discuss about the general register organization. Okay, before I go on to that, please see what is the job of the control unit. The job of the control unit is basically to control, okay, or overall, you know, exert overall monitoring of the operations which are done in the ALU with the help of registers. That means the entire execution of the instructions is controlled or supervised by the control unit. Now, how this happens is also what we are going to look at in today's class, right? So let us start with the general register organization. So this same block diagram that you've seen here, now we are going to see this in a very in-depth, we are going to see that at a very in-depth level. Please see. Now, what you see on your screen right now are 7 registers. Okay, 7 registers. Okay, the ones that we have talked about earlier, right? And now, so we have, the first thing is that these registers must be connected with the ALU, right? They must be connected with the ALU somehow, okay? Now, how to connect? So we could have had a direct connection of each register with the ALU, but you can only imagine that with an increase in the number of registers. As we've discussed, this is just a basic computer and we are using a very limited number of registers here. But as the number of registers increases, especially so in the current architectures that we have in the market today, these one-to-one connections, if we make, for the registers to the ALU and all other units, then you can just imagine yourself how large this circuitry would be and how complex this would become, right? How complex such a circuit would become. So it will be complex to construct and then debug if there is a problem and all those things, right? So that is why we look forward to a bus kind of a system, okay, for connecting the registers with the ALU. This is the same logic, if you remember, we had looked at when we had discussed the bus system in chapter number 2. Okay, so due to the same reason. So please see now, this is inside the CPU. What are, how this interconnection is being done, how these buses are made, please see. Now, each of these registers, the output of each of these registers is connected to a multiplexer. Okay, so you see two multiplexers here. Let's first focus on this first multiplexer here. Okay, so this multiplexer will receive an input from the output of each of these registers, right? So how many registers are there? 7. So what would be the size of this multiplexer? That is required here. Who will tell me? Who will tell me? Please see what is the size of a multiplexer. We have a we always have the size of a multiplexer is always 2 raised to the power of n cross 1. Yes, who was this? Yes, who was this?
What?
Yeah, you were trying to answer.
No, ma'am.
Okay, so the size of the multiplexer is always 2 raised to the power of n cross 1. So what this means is that I have a 2 cross 1 marks or a 4 cross 1 marks, then 8 cross 1 marks, then 16 cross 1 marks, and so on and so forth. In this case, since I have 7 inputs which need to go into this marks, so which marks I should use? I will have to use 8 cross 1 multiplexer. Okay, so I will be using a 8 cross 1 multiplexer. Now I have 2 multiplexers here. What is the purpose of having 2 multiplexers here? These registers actually store operands in them. Okay, so if I have to do a certain arithmetic or logical operation on the operands which are stored in the registers, then those 2 operands, let's say most of the operations are binary, right? So plus is a plus b, c plus d, and so most, assuming that most of the operations are binary, we take the operand of these registers and feed them into the multiplexers. So the first operand goes to the first multiplexer and the second operand goes to the second multiplexer. Okay. Now, out of these registers, which operand, which register stores the operand is operand 1 is told by the select A lines. Okay, so if this is a 8 cross 1 marks, we know that it will require 3 selection lines, right? So which out of these 7 registers has the operand 1 is specified by select A, then the operand 2 is stored in which register is specified by selection B. Okay, so three bits here tell us which register has operand B. So that particular register is of operand that is storing operand 1 is passed on to bus A, and the register containing the operand B is its input is selected and passed on to bus B. Okay. Now these two buses form the input of the arithmetic and logical unit. Now we have 5 input lines which are going to this ALU. These 5 input lines determine which operation, which arithmetic or logical operation will be performed on these two operands. Okay. And the output of the operation can then either be passed on to the user on, let's say, the monitor or printer, that means some output device. Okay, or it can be stored in one of the registers again, so that, for example, I am doing a competition such as A plus B into C. So I have just now computed the intermediate result A plus B. I want to store that result back in one of the registers, and then I want to compute A plus B. I already have into C. Now I want to do, right? So I may like to store the result back into one of these registers. Now, which register to store the result in? That is specified with the help of this 3x8 decoder which is present here. So we give it 3 input lines, okay, and accordingly it selects one of these registers. We know that this has 8 outputs, right? So each output is connected to one of these registers, and accordingly, if, for example, 001 is active here, then the first register will be selected. If 0010 is active here, then R2 will be selected, and so on and so forth for storing the result of the computation. Okay, so this is how this actual communication between the register set and the ALU is taking place. Okay. Now, how is the control unit supervising? That means, telling, first of all, what operation is to be done. That is a part of controlling the operation, right? So what operands are there? In which register are they stored? Then what operation is to be performed, and then where the result is to be stored, right? If the control unit issues a command regarding, that specifies all these things, okay, that what are the operands in which registers are they stored, which operation is to be performed, what is the destination register, okay, and that is how it is able to this kind of a command is known as a control signal, and this is how the control unit is able to control the entire operation, because it is specifying everything about the operation, starting from where the operands are located to where the result should be stored. Is this clear? Is this
Yes,
clear?
ma'am.
Right. So please see this this entire control signal, or actually we call it a control word. Okay. So this entire control word actually consists of what? It actually consists of, please see, cell A. So selection lines A, because they tell us which register the operand 1 is stored, cell B to tell us where the operand 2 is stored, then the cell D to tell us where the result should be stored, and 5 bits for OPR which tell us which ALU operation is to be performed. Okay, is this clear? So together, this word is called the control word. And you must also remember the order in which these fields are placed. The 3-bit cell A comes first, then the 3-bit cell B, 3-bit cell D, and then the 5-bit OPR. Okay, so this is what you have to remember in this sequence only. Okay, now please see how many operations will be possible if I have 5 OPR bits here. Who will tell me? We've done this so many times. 2 raised to the power of
5.
5. Okay, a maximum of 2 raised to the power of 5 operations can be supported using the CPU. So these are very important questions. Please see, especially in the OBE kind of, earlier also they used to come, and now they are very important. So what will be done is, the number of registers, if I tell you that instead of, 7 registers, there are 15 registers or 14 registers or 16 registers. So any number which is greater than 8 and less than 16, what will be the configuration of the mux that will be required? It will be 16 cross 1, right? And how many selection lines will be required then? 4, right? Similarly, 16 cross 1 multiplexer here and 16 lines here. Okay, and then again, obviously, because there are, let's say 14, 15, 16, whatever number of registers are there. So what will be the configuration of the decoder that will be required? We will require a decoder which will have 16 inputs. So that will be a 4 cross 16 decoder. Okay, and how many inputs will go into that? 4, obviously, right? So there will be 4 bits in cell D as well there. Okay, and they will tell you either, that it only supports 4 operations. So how many bits will you put in the OPR field then? Only 2. Okay, so it will be 4, 4, 4, and 2 then. Okay, so this will be the construction of the control word. So this is the first kind of question that you can expect in any of the theory exams or viva. Okay, so this is this diagram, and this is also known as the general register organization. This is very important from the examination point of view as well. Okay. Now, please see. So suppose please see that, this is another kind of question that is generally asked. So they give you this kind of a micro operation or a micro instruction, and they tell you that please construct a control word for this. Okay, so please see, if the registers are, if the bits for the selection lines are corresponding to the names, to the number of the register. For example, for R2 it will be 0, 1, 0, right? For R3 it will be 0, 1, 1. Okay, and then cell D will be the destination register. It will be R1, so 0, 0, 1. Okay, so they will, you have to just substitute these binary codes corresponding to the register numbers to get cell A, cell B, cell D. Okay, and then OPR is generally given to you. Either it will be directly specified in the question, or they will give you a table of this sort. Okay, so what is the operation that is being done here? The operation is subtraction. So I go here and I look for subtraction. The opcode is 0, 0, 1, 0, 1. Okay, right. So I come here and I put in 0, 0. You can see this 0, 0, 1, 0, 1 here. So this entire set of 14 bits now taken together is the control word. It is my control word. Is this clear to everybody? This is very important.
Yes, ma'am.
Yes, ma'am.
So please practice formation of the control words from table 8.3. Okay, although it is very easy, but then you should just practice. Okay, now another thing that I want to discuss with you today is what is a stack. Okay, now you have already studied, you've already looked at arrays in C, C++, whatever language you've done, right? So, what is a stack? You remember when we were doing the bun instruction and the BSA instruction? We had to store the last address, that is the return address, right? So always, we used to fix up a position. Let's say memory, when we were talking about the interrupt, then we went to memory location 0 and we put the return address there, right? And so we were just supposing the place to store the return address somewhere. Now, an alternative to that is usage of a stack. What is a stack? Stack is a LIFO. LIFO means a last in, first out. So let me take an example. For example, if you are coming to college every day, so Monday you wear a blue dress, then Tuesday you wear a black dress, then Wednesday you wear a green dress, and then red and then orange on Friday, right? Now, every day when you go back to your home, there is a sofa and you just, take off your clothes and throw them on that sofa. Right. So on Friday, when you look at that sofa, that, oh, today mama is going to, scold me like anything if I don't sort out my clothes. So what will you find? The orange dress which you wore on Friday was on the top. Right. It is on the top, followed by the red one and then green and then black and then blue. Right. So the dress that came last was on the top of the stack. This is known as a stack. Stack is when you just keep on throwing the items one over the other. This is known as pushing. Okay, when we add items to a stack, it is known as pushing. Why pushing? Because you are always adding an item on the top of the stack. Okay, at the end of at the top of the already added items. Okay, and therefore, when you remove the items, the addition and deletion of the items is only allowed from the top. Okay, so the only element that you can access is when you start removing is the top element, which has actually come in last. So last in, first out. This is what is stack. Now, why use stack? Stack is very useful for storing the return addresses. Please see. So I am, let's say, executing a program A, okay, and I get a interrupt and I have to go to program B. So I need to store the return address of program A, right? So I store it at the top of my stack, right? Now, suppose multiple interrupts are allowed. So from program B, I again get a interrupt. I go to program C. Now I store the return address of program B. Again, it will be on the top of the stack, right? Now from program C, then I go to program D. So I'm saving the return address of program C again on the top of the stack. Now when I want to, I've done completed program D and there is no further interrupt. I want to complete program D and come back where? First of all to program C, from where I was called into program D. So the first return address that should be retrieved automatically should be of program C, then program B, then program A, right? Last in, first out, right? And this is exactly what a stack enables me to do. Okay, so in your next semester, when you do your data structures, you are going to see a implementation of the stacks, okay, using arrays as well as using uh, linked lists, okay. But right now here only this concept is important, that what is a stack, it's a LIFO, where it is used, and the additions and deletions are always allowed in the stack only from the top, and that is why we always just need to keep track of one special location, that where is the top located. Okay, so initially when my stack was empty, the top was 0. Okay, when I have one item in my top stack, then the top is 1, and so on and so forth. This location of the top is known as stack pointer. It is known as a stack pointer. Okay, so this section 8.3 is only up till here, or maybe up till this page, up till here in your syllabus, right? What is a register stack? A register stack is a set of registers which are arranged in a fashion in which you can always, one over the other, in which you can always add or data or remove data only from the topmost register. Okay, so that is a register stack. Okay, so again, as I said, stack could be implemented using arrays or linked list or maybe registers. Okay, so that is the implementation. You don't need to go into those details right now, however. Okay, so
Mom, could you please,
after this, yes,
Mom, could you please repeat
yes,
what register stack?
come again, please.
Mom, please repeat register stack.
So register stack is a set of registers placed one over the other, where the data can only be inserted or deleted from the topmost register only. Okay, that is not in your course right now, but you can read about it if you feel like. So, as I told you, a stack could be implemented using arrays or linked lists or registers. So, when it is implemented using registers, it is known as a register stack. Okay, the concept remains the same. Now, I'll take 2 minutes to discuss the implementation of the instructions that you told me last time. The skip, you were talking about the SPA, skip if positive AC, skip if negative AC instructions, right?
Yes, ma'am.
Just give me a minute, I'm just starting sequencing. Let me know when my screen is visible to you.
It's visible, ma'am.
Right. So how to make the skip if positive instruction? Let's see. So I'll add a new instruction here. Let me call it SPA. SPA means skip if positive AC. So if the value of AC is positive, then I skip the next instruction. Okay, whatever is the opcode given in your list, you can type that here. I'm just leaving this right now. Okay, and so this will be OP, I think, right? Here, okay, so let us look at the implementation. So how will we implement this instruction? So there is a test instruction here. Please see. I'll say new, right? Test instruction, micro instruction, right? Now How do we get to know whether the value of AC is positive or not? So if the 15th bit, that is the most significant bit of AC, is positive, it is 0, then the value of AC is treated as positive. If it is 1, then it is treated as negative. We have discussed this, right? So let me call it SPA again. I'll say which register we want to check. The accumulator. What is the start bit from which you want to start the comparison? I want to compare the 15th bit, right? How many bits do I want to compare starting from the 15th bit? Only one, that is the 15th bit. What do I want to compare it with? I want to check whether it is equal to, not equal to, less than, greater than, less than equal to, greater than equal to. Okay, is this clear? Right? Terminology, right? I want to check
Yes.
whether it is equal to 0, right? If it is equal to 0, I want to omit. I want to omit. This will automatically skip one instruction. Okay, so I want to skip how many instruction? One instruction. So I'll say okay. So that is it. And now we will just transfer this here and then say end. Right? That is it. Now, when we want to implement skip if negative AC, the only change I will need to do is that here I need to compare its value with 1. Then it will become skip if negative AC. Okay. Now, let me show you SZE or SZA. Skip if 0 AC.
The child.